Hello everyone, and thanks for watching Edupedia World Videos. This is the second video for the topic electromagnetic waves and the final video in the broad concept of electromagnetism. Up till now, we've seen the mathematical and quantitative aspect of electromagnetic waves to some extent, and now we'll see how electromagnetic waves generally behave in nature. What we do know about electromagnetic waves is they have some characteristics, the electric and magnetic field magnitudes, and also most importantly the angular frequency from which we can calculate other wave-like things such as frequency and wavelength. We know that frequency and wavelength are related by a factor of the speed. Right. The waves which have the longest wavelength and the shortest frequency are radio waves, and the largest frequency are gamma rays. This variation mathematically is a lot because radio waves can have wavelengths as large as 30 kilometers, and gamma rays can actually have wavelength as small as 10 to the power minus 16 meters. Right. And as when it comes to frequency, the lowest frequencies we know are of the order of 10 to the power 0, that is 1 or 2 cycles per second, and they can go up in gamma rays to 10 to the power 24 cycles per second. Right. So we see mathematically there is a big range of frequencies and wavelengths that we can have in electromagnetic waves. Radio waves are the lowest frequency waves, and they are produced by charges accelerating in alternating current circuits. In an AC circuit, when you have an inductor and a capacitor, then you may produce radio waves due to acceleration of charges. They are used in radio and TV communication. Right. You next have microwaves, which are used obviously in your microwave ovens, but they are also used in radars in many communication systems. They are also produced by electric circuits in which you have oscillating currents. We studied alternating current in a previous chapter. Then you have infrared waves. Infrared waves generally lie between this and this region. They are the waves which have the frequency just below the frequency of visible light, and they are mainly emitted by hot bodies. The rays can be used in physical therapy, and you might have heard of the infrared camera, in which you can look at something and you'll see a map of the heat, in which red will denote hot and blue will denote cold. The redder a region is, the hotter the region is, and so on. So that's why infrared is generally associated with heat, because whenever you have a hot body and it emits electromagnetic waves, the wavelength and frequency are such that it generally falls in the infrared category. The most familiar to us obviously is this really narrow and small region which we refer to as visible light. Visible light has wavelengths in the range of 380 nanometers, that would be violet, to 780 nanometers, that would be red. Violet has the lowest wavelength and the highest frequency out of all visible lights. Red has the lowest frequency and the highest wavelength. If any object emits electromagnetic waves and the wavelength or frequency lie within this region, then we will be able to see that object emitting a certain color. That is why we say that any electromagnetic waves within this region can be directly seen by the eye. We cannot see the one previous to that, infrared waves, and we cannot see the next one, ultraviolet waves. Ultraviolet waves are emitted by the sun and many other regions, and they can be harmful for us. Right. In fact, the ozone layer in the atmosphere, which we'll see in a second, is mainly there to protect us from ultraviolet radiation. Next you have X-rays, and you know the most important property of X-rays. It can cleave through skin, but it cannot cleave through bone. So X-rays can be used in medical diagnosis. Right. Finally, we have the lowest wavelength and highest frequency waves called gamma waves. And gamma waves are actually emitted by nucleus. Just like ultraviolet and visible light can be emitted by atoms when an electron goes from one state to another, in nucleons in a nucleus, when they go from one state to another, they emit much higher energy and much higher frequency rays, and those rays are called gamma rays. And gamma rays have the shortest wavelengths of all the electromagnetic waves we have to deal with. So with these, we see this incredible phenomena that all these electromagnetic waves, from radio waves to visible light to gamma rays, have different uses, different properties, but mathematically they're all the same. The only difference between them is a number which denote how many times they repeat in each cycle. If the frequency is on the lower side, then you have radio waves. If the frequency is on the extremely high side, then you have gamma rays. Now there is one final thing which is left in this chapter, and that is to study the composition of the Earth's atmosphere. So let's say this is the surface of the Earth's atmosphere, that is at a height of 0. Then from the surface up to a height of 12 kilometers, I'll not draw these figures to scale. I won't even draw this actually. I'll just make an axis like here. From 0 up to a height of 12 kilometers is a layer, the lowest layer, which we call the troposphere. It is the lower layer of air and it stretches from the surface to about 12 kilometers. Most water droplets, water vapor, ice particles and the other things which form clouds which ultimately give rain, all of that happens within the troposphere. The density of air decreases as we go up, and it decreases so drastically that even at the top of the layer, the density is about 1/10 of what it would be at the bottom of the layer. So by the time we go 12 kilometers up, the density is decreased by a factor of 10%. Decreased by a factor of 10, not 10%. Right. After this, the next layer, ranging from 12 kilometers to 50 kilometers, is called the stratosphere. The density at the top of the stratosphere is 1,000th. The density at the top of the troposphere is 1/10 of the density it was here. If this is 1, this is 1/10. The density at the top of the stratosphere by the time we reach there is 1,000th of the density at the surface. So it's a pretty remarkable decrease. In the upper part of the stratosphere, we have something which you probably know about. It's called the ozone layer. After 50 kilometers to a height of 80 kilometers, we have what is called the mesosphere. And from 80 kilometers up till the top, the atmosphere of the Earth extends approximately up to a height of 300 kilometers. Though the density here is incredibly small, this whole region, the topmost region of the Earth's atmosphere, is called the ionosphere. You don't need to remember these values, the heights of them and the densities. That I'm just showing you to illustrate to you how density decreases. But you do need to remember some small things such as troposphere has all the clouds, stratosphere has the ozone layer, and so on. There are no sharp boundaries between the above divisions, but the numbers given, they're only a rough guide, and approximately to these heights we define the layers to be such. The main source of electromagnetic radiation in all our atmosphere is the sun. That is the one thing that is external to the earth, and that is the one thing that gives us all our energy, right? Apart from some energy that might come from stars. The sun sends electromagnetic waves, but they consist of a variety of wavelengths. They consist of infrared light, ultraviolet light, visible light, and many other wavelengths. Visible light is very weakly absorbed by the atmosphere and it reaches the ground, and that's why we're able to see things around them. Other portion of lights are very strongly absorbed by the atmosphere, and that is one of the reasons we can support life on the Earth. In fact, anytime we start looking at life in other planets, we start looking at two things. The primary thing is water, but the next thing is the atmosphere, because an atmosphere is needed to maintain the temperature and to reduce the radiation coming from the sun. So most of the radiation will be absorbed by the sun, most of the visible light will get through, most of the infrared radiation will be absorbed, and that will be used to heat up the atmosphere. That's why the temperature on the Earth is much more than the temperature on what would have been Earth if there were no atmosphere. In that case, all the heat would have escaped and we would have had a much colder planet. So irradiation, infrared, is absorbed by the Earth atmosphere and is used to heat up the atmosphere. The ultraviolet radiation is absorbed by the ozone layer, and that's why the ozone layer is very important. Ultraviolet radiation, when it directly falls on us, can cause many diseases, and the ozone layer absorbs most of the ultraviolet radiation. In the 80s and 90s, there was actually a big worry in the environmental society where people knew that we had a big hole in the ozone layer and that might lead to some problems. Right. This completes electromagnetism. Thank you.